Good afternoon, everyone. Thank you for coming to the MTL seminar. So my name is Luqiao Liu. So today we are very honored to have Dr. Stephanie Hernandez to visit us and give us a talk. Dr. Stephanie Hernandez got her PhD from University of Minnesota in electrical engineering. Since then, she has been working for different departments at Seagate, and most recently, she has working in the research department of Seagate, particularly on advanced storage and memory devices. So now she is a senior director for the storage and memory group. So without further ado, let's welcome Stephanie.
All right, thanks, Luqiao. Super excited to be here. Was at MRS most of the week, so it works pretty well to come and talk to you guys today. My goal today is to convince you that the data storage industry has a lot going on and a lot of interesting research, and I'll share some of it with you today. I'll talk about heat-assisted magnetic recording. Now, hard drives have lasers in them, and that's super cool, so I'll explain why we need those to keep increasing the storage capacity of hard disk drives. But most of the stuff that I'm going to talk to you today, I obviously didn't do on my own, so I want to acknowledge my team. I have a very strong team of people who do experiments, who do modeling. I've got one of my guys sitting on the second row, Sergio, but most of these guys are in Minnesota right now. And of course, we have a lot of different groups all over the US and actually all over the world that do R&D on the recording heads, recording media on the systems. So everybody has contributed a significant amount over the last couple decades to make HAMR a reality. And I'm from Minnesota, and I want to convince people out here on the East Coast that Minnesota is a hub for innovation, and we have a very strong research group in Minnesota. My team is responsible for understanding what the 10-year HDD or hard disk drive roadmap looks like. But we also have some research going on in the emerging memory space. We're looking at archival and alternative data storage technologies. We're looking at the photonics, optical devices, biosensors, and a lot of other alternative technologies. We have the recording head operations in Minnesota. It's a very large fabrication facility that manufactures most of the heads that are put into our Seagate drives. And there's very strong design teams there. Other locations in the US include the recording media operations in California, the drive integration going on in Colorado. There's research into systems and data structures and data security also taking place at Seagate. Seagate's main concern is how do we keep supplying the data storage needs of the world. The International Data Storage I forget, it's a company or whatever. They estimate that the global data sphere, which is the amount of data that the world will create, will triple between 2023 and 2028. So 394 zettabytes of data will be generated in the year 2028. Now, a zettabyte doesn't really mean much to most of us. But we know what a terabyte is. I can go to Best Buy and buy a 5 terabyte drive, and I think I can store 100 hours of 4K video and 1 million photos in a 5 terabyte drive. The drives that we sell to our big customers, they're 30 terabytes. So that all makes sense. So if this terabyte is the invisible speck right here, a zettabyte is this giant cube, which is 1 billion terabytes. So 394 billion terabytes are going to be created in the year 2028, but only 19 zettabytes of that data will be stored in drives of any kind, because that will be the available data storage in the year 2028. And actually, most of that data will be stored in hard disk drives. And I'm going to steal a line from my boss. He always says that he can't think of any device that has as much technology as a hard drive. This morning, I asked ChatGPT if it knows any other device that has as much technology as a hard drive, and it told me a smartphone. And I'm like, we will argue about this later, but I still believe that a hard drive has much more technology than any other device out there. You know, hard drives have looked the same over the last 50 years or more. They're basically a disk that contains the storage medium. There's this mechanical arm at the end of which are read and write transducers. There's motors that spin the disk and move this arm along the radius to be able to write the data wherever it needs to be written. And although the device, you open up a hard drive, it looks the same over time, the technologies that go into these different components have evolved significantly over the last decades. And we've undergone quite a large technological transition even right now. So in a hard drive, there's mechanical components, there's optical components, there's magnetic components, there's plasmonic components, electrical components, and all of them, they have to work together to be able to read, recover, and write information at very high areal densities. So if we look at the very tip of these arms are the read and write transducers. So the critical geometries for these are on the order of tens of nanometers. The disk contains the storage medium, and it's made of a granular magnetic material. And these grains are on the order of less than 10 nanometers, and each bit is less than 10 grains. The distance between the head and the disk is on the order of a nanometer. And so this mechanical contraption has to ensure that there is 1 nanometer, on the order of 1 nanometer spacing in between the head and the disk. The disk is spinning at 7,200 RPM. So if you were to stand at the edge of the disk, you'd be going over 60 miles an hour. And so one analogy that's been said a lot is, pick your favorite jumbo jet. A hard drive, how a hard drive functions is essentially like a jumbo jet flying over the ground at an inch above the ground, trying to resolve every blade of grass. So it's pretty awesome, right? And I'd like to show more images and wow you guys with the scale of a hard drive. And so these are cross-sectional images of the writer, which is this structure up here, and the media. So this is the storage layer, or this granular storage layer, also a cross-sectional image. And the distance in between them here isn't really the nanometer, but it's supposed to be less than 2 nanometers, which is not large enough to fit a DNA strand. This is a picture of a magnetic writer. So the entire structure fits within a red blood cell. Really, the active element is this little bit down here. This is the end of the arm that's holding the head over the disk. And this structure right here is the slider, which contains the writer and the reader and all of the elements necessary to make these devices work. And if you just place this slider on top of a penny, it is smaller than Lincoln's nose. Now, we think of, hard drives the device looks very much the same, but the geometries of these different components have significantly changed over time. And this is around a 20-year time that we're looking at. This is the magnetic bit size, the reader, and the writer. Around the year 2000, we were at 10 gigabit per square inch. So I will talk about areal density, which is bits per square inch, but I'll also talk about capacities. So I'll say, right now we're shipping drives at 3 terabytes per disk. So just so you guys understand some of the language. Right now, this number right here is physically how many bits are in 1 square inch. And there were 10 billion bits back in the 2000s. And the geometries were, on the order of a micron to half a micron. If we go to the year 2020, for example, around 1 terabit per square inch, so 10 to the 12 bits per square inch, we're talking 50 nanometers and below type of geometries. And yes, it is the physical dimensions of these devices that have led to these drastic increases in areal density, but also the technologies are fundamentally changing over time. Around the year 2000, we went from longitudinal magnetic recording to perpendicular. Longitudinal magnetic recording means that the magnetization of the media was in plane, as opposed to perpendicular, where it was out of plane. So that led to a significant increase in areal density. Sometime after the year 2000, we went from giant magnetoresistive sensors to tunneling magnetoresistive sensors. And before that, many years before, they were inductive. So there's all of these technological leaps that were necessary in order to even enable these significant reductions in geometry size. And now if we look at 3 terabit per square inch, which is kind of where we want to be close to the end of this decade, we're talking about bit sizes that are 20 nanometers, then the largest dimension, which means I need a writer that's 16 nanometers wide and a reader that's 13 nanometers wide. The problem is if we stick to perpendicular magnetic recording, which means that I'm using magnetic writers to write the information. If I make these writers very, very small, then I lose the magnetic field that's available. So going to very high areal densities is just not possible with the current technology. And so I talked about, yes, the data explosion is coming and we need to do something about it. We need to be able to provide storage solutions to store as much of this data as possible. We can't make the HDDs physically larger. There's a limit to the amount of space data centers have. So the information stored on hard drives has to be physically smaller. And I mentioned how in the media, each bit is a collection of grains. And so if you look at this little piece of media here, the head is the element that writes and recovers the information. And it moves in this direction. And it magnetizes these different bits by changing the polarity of the writer to each of the 2 different directions. So when I talk about we need to increase the density of the information, or the areal density, that means I'm making these bits smaller, and this is a track, and I'm writing these tracks closer and closer together. And we measure this areal density in terms of terabits per square inch. The main problem we're trying to solve here is, let's say this is some other picture of a granular media. And I have a 16 terabyte drive, and physically, this is what a 16 terabyte, a bit for a 16 terabyte drive looks like. if I want to fabricate or make a 32 terabyte drive, if I don't decrease the grain size and decrease this bit size, then there's fewer grains per bit. And this is problematic, which I'll explain in a minute. But we are going through a technological transition. We've actually started shipping drives with this new technology called heat-assisted magnetic recording. Most of the drives out there in the world are perpendicular. Like I said, they're written by a magnetic writer. The magnetic moment in the disk, the media, is pointing up or down, so it's perpendicular to the disk. Heat-assisted magnetic recording has all those same components. The media is still magnetized up or down relative to the plane of the disk. There's still a magnetic writer that supplies the excitation needed to switch the magnetization of these media grains. But there's an added element. It's an excitation, a thermal excitation that aids in the switching process for this new media that we need in order to keep increasing the areal density. The main problem, like I said, I need to decrease the bit size, which means that I need to decrease the grain size. If I don't decrease the grain size, and I have fewer grains per bit, and the grains are big relative to the bit size, the transition in between two different bit polarities is not going to be very straight. And this is a significant source of noise. So the media SNR is proportional to the number of grains in a bit. So our goal is to try as much as possible to maintain the number of grains per bit, even though that's actually quite difficult. But the goal here is, yes, we need to decrease the bit size. However, small grains are susceptible to thermal fluctuations. This material is a magnetic material, and magnetic particles try to switch their magnetization with a frequency that depends on the temperature, it depends on their volume, and depends on their magnetic anisotropy. So if I don't change anything else in the media and just decrease the grain size or particle size, these grains will attempt to flip more often, and that's not good because I need my data to be stable over many years. So one way to maintain the stability or increase it is to increase the magnetic anisotropy, which is just a measure of the magnetic hardness. And there are materials that have high anisotropy, but they're difficult to write if I just have a magnetic writer. And there is a limit to the magnetization that's available in the materials that we know of. And especially as we try to decrease the size of the writer, as we're trying to decrease the size of the bit, that available field decreases significantly. So we can't just increase the anisotropy. We need to now provide an assist method that reduces this magnetic anisotropy, but only during the write process. So like I said, magnetic materials tend to lose their magnetization at high temperatures. So we can leverage this only during the write process and still have media that is very, very thermally stable at room temperature. So now we have, in addition to a magnetic writer, we have plasmonic elements, we have lasers that provide that excitation to be able to write the media. This is a picture if you're laying on the disk looking up. We still have a magnetic writer, that's this element right here. And now we have a near field transducer. So we still have the magnetic writer, but now we have a laser. And we need a waveguide to bring the light from the laser down to where the disk is. And we need to convert far field light to near field light. So we implemented a near field transducer, which is a plasmonic material that converts that incident light to surface plasmons, which travel toward the disk, the air-bearing surface. And they are concentrated at this peg, which is placed right at the air-bearing surface. So there is a thermal spot created in the media that's as large as this peg. And we can make this peg pretty small. So now the bit size is determined by how small we can make this peg. And the thermal spot that's generated in the media can be quite small and at very high temperatures, so above almost 400 degrees C. And the thermal gradients, which are really important to us, so how fast the temperature falls off, is very significant for these thermal spots produced by the NFTs. So the media has to be different, and that's the whole point of HAMR. Now we can use very high anisotropy media. So this plot here is coercivity. So that's the field at which a sample will have effectively zero moment, which is a measure of how much field do I need to switch the magnetization of a material. For iron platinum, which is the material that we're using for HAMR, the coercivity is extremely high, over 80 kiloersteds, which is 10 times larger than that of what we're able to write with perpendicular magnetic recording. But if I apply a very concentrated thermal spot, then the coercivity is reduced to almost zero. And just enough to be able to write it with these fields that are applied by the magnetic writer. So a HAMR drive, you open it, looks like a regular hard drive, but the inner workings of it are very different from perpendicular magnetic recording. We need a laser diode, needed to develop an entire waveguide structure, invented a near-field transducer, and integrated that into the recording head. Brand new media needed to be developed. With any new hard drive generation, you need updated firmware. You need to modify the manufacturing process, both for the head and the media and the drive, to accommodate HAMR technology. And there's like a gazillion things that you need in order to implement revolutionary new technologies to a device that, to the naked eye, looks exactly the same. And the only reason a company like Seagate is willing to put in so much investment and time and money and resources to integrating some new technology is because it enables a brand new S-curve. So it's not just a one-time gain that HAMR gives us. It enables an entire generation of products, and we can imagine that the capacity, we can more than double the capacity relative to what HAMR gives us today. Compared to PMR, with HAMR, the writability and the track density is no longer determined by the geometry of the magnetic writer. It is determined by how small we can make the NFTs, and we can make NFTs really, really small. HAMR also allows us to have higher linear density because the downtrack resolution is now determined by this measure that we call thermal gradient. So this is the temperature rise in the media as a function of the downtrack direction. So this measure is called the thermal gradient. So the temperature drops off very quickly, so that means we can write very sharp transitions. Add to that we can use smaller grains, which enables us to write sharper transitions. We've actually demonstrated, Seagate's actually demonstrated 5 nanometer grain size media. It's not something we can put in a drive today because it's experimental, may not be completely reliable yet, but it has been demonstrated and the media teams are working on that. So yes, HAMR enables much higher areal density than previous technology, and now we're just trying to figure out what else do we need to keep scaling the areal density with HAMR before we need to move on to some much more advanced technology. And one activity that we do in our group are areal density demos. So all of this data is produced by a a test platform called a spin stand, which is basically like a large drive. And you can swap heads and media very easily, very quickly. So you can test out very experimental heads and combine the ones that give you the best performance. This plot right here is the y-axis is the track density in kilotracks per inch. And the x-axis is the linear density, so how small my bits are along the track, which is kiloflux changes per inch, or you could say kilobits per inch. And each of these different points is a different head media combination. And the green points are SMR, the blue are CMR, shingled versus conventional recording. I'll explain what that is shortly. So where we are right now is up here. These are lines of constant areal density, and this point is the 3.5 terabit per square inch areal density line. And we exceeded that with shingled magnetic recording. And what that means is that this is equivalent to a 6.2 terabyte per disk capacity. So hard drives have 10 disks. Our mass capacity drives have 10 disks. So it would be equivalent to having a 62 terabyte drive. We're selling 30 terabyte drives to our big customers. So we can demonstrate double the capacity, double the areal density that we're actually producing today. This is a real experiment. This is real data. Even though these are experimental heads, they may have different features that we can't just put it in a drive and sell today. They may not meet the customer reliability requirements, but it demonstrates, it's a proof of concept of how small can we actually write data. And this is very, very small. These are bits that are smaller than 10 nanometers, like 8 nanometers in one direction, and more than 1 million tracks per inch. These pictures were taken when nobody would believe that HAMR was a real thing. So these are magnetic force microscopy images of HAMR tracks, just zoomed in. And kind of outdated, but cool to show. And it shows, a unique feature of HAMR patterns. It shows the curvature in the transition. We have a heat spot, and the heat spot determines how the bits are written. So this curved transition is a unique feature of HAMR, which is not present in perpendicular. I talked about CMR, SMR. I'll explain what that is. So conventional magnetic recording is what most drives out there are. And it just means that I'm writing tracks along the disk. And I can write any track at any given time. I can write them in any order. And there's no overlap in between them. Shingled magnetic recording is different in that there is intentional overlap, which allows you to really bring those tracks together and increase the track density. Now, they overlap, so I can't just rewrite any track whenever I want. There is a specific order that must be followed. And a disk is divided into zones or bands. And in order to rewrite one of these tracks, you need to erase the entire band in order to do so. So from a system level perspective, it's more complex. But in some cases, maybe some customers want to do something like this for certain use cases because it does really allow you to push the track density. So it's an areal density enabler. And then there's this other idea called interlaced magnetic recording, where you have two different types of tracks. You have wide ones that are written first and narrow ones that are written in between the wide ones. And the idea here is that I'm writing a very wide track, so I can make the bits actually small for these wide tracks because I have so much better resolution in the writer when I'm writing at higher temperature. And then you have these narrow tracks on top that don't see any influence from adjacent tracks because they're written after the wide ones and they're far away from the other narrow ones. This is an even more complicated system because you can't really erase the wide ones anytime you want. So this is not yet in a product, but it provides even more areal density gains relative to shingled. And we have this other scheme called multi-sensor magnetic recording, which can be used with any of these others. It just means now I have 2 read sensors in my head. The reason I want 2 read sensors is because read sensors are made up of magnetic materials, and magnetic materials can be thermally unstable if you make their volumes too small. So multi-sensor magnetic recording allows you to average the signal from 2 different readers. So I can use narrower readers than I would otherwise be able to. So MSMR, multi-sensor magnetic recording, is actually in products out there today. Some people call it 2-dimensional magnetic recording, but it really just is reader averaging. And this is just data again, kind of old data, but it shows this is areal density. Sometimes we go terabits per inch, gigabits per inch, but hopefully it's not too confusing. And each of these are the areal densities for CMR, conventional, shingled, and interlaced. And the subcategories are 1 reader, 2 reader, and 3 reader. So for the experiment, we don't actually have heads that have 2 readers or 3 readers. In the experiment, we just do multiple read passes and average out the signals. So it just shows how you can significantly increase the areal density by doing these advanced recording schemes, and that multiple readers can really help in increasing areal density through that reader noise averaging. And this is just newer data. So the older data, the max was 1.9 terabit per square inch, but in newer data, we're getting much closer to 2,500 gigabits per square inch, or 2.5 terabit per square inch. These are not demo numbers. These are heads run at more normal conditions. My background is in modeling, so I need to talk about that a little bit. And Seagate uses modeling very extensively. So model is simply, you run a simulation based on some governing equation under some conditions. And there's a lot of groups at Seagate that use modeling to inform design. There's the mechanical guys who do air bearing modeling, or the writer designers model the NFT thermal and optical properties. My group does micromagnetic modeling of the recording process. So what we try to do is mimic every part of the recording process. We have the write process, the read process, and then what happens to those signals after you've recovered them. They go through a channel and they become data. And so this is a bunch of different models that are used in order to capture all of these different features. To simulate the write process, I need all of the media properties, the grain size, the magnetic properties. I need the properties of the NFT, the thermal properties, the heat spot it provides. I need to know the field that is supplied by the writer. And so this allows us to write patterns, simulated patterns, and then we need to do a reader simulation to capture these patterns into signals that we use to extract metrics that we're interested in, for example, the SNR and the bit error rate. So these simulations can be quite time-consuming, and we've done a lot of work to accelerate all of these. We're working on using AI to accelerate some of these physics simulations, or to generate surrogate models that allows us to pinpoint this is the space that we're interested in. And we have GPU clusters that allows us to run these simulations much more quickly than we were able to in the past. But this allows us to provide design direction to, for example, the head designers. it takes months for a head to go through the entire fabrication process. It's thousands of steps. Some of them are fabrication steps, some of them are metrology steps, but it takes many months to go from wafer substrate to a full-fledged head. And then we need to take these wafers and slice them into components, into individual heads, and then put them in drives, test them with media, and then once we have data, it's more than a year. So simulation, not just these kind of simulations, but any kind of simulations, gives us a clue about these are the designs we need to pursue, these are the components that we need to be building. So Seagate is very much focused on how to use simulation more and more to help guide design as the designs become much more complex. And I guess I'm running a little bit short on time, but I just wanted to highlight that for magnetic simulations, the most accurate way to do it would be to model each of the individual atomic spins. We, in general, do more of a mesoscopic approximation. Atomic moments are tied together by a property called exchange. So nearby moments have the same magnetization, and we can use this to increase the cell size of the simulation. But with HAMR, we can't do that anymore because we're operating at very high temperatures, close to the Curie temperature, which is the temperature at which magnetic materials lose their magnetization. So nearby atomic moments are actually randomized. So they're not all pointing in the same way. But if I wanted to model an entire data sequence with hundreds of bits, I really can't do that using an atomistic simulation because it would be billions of atoms, so it would take too long. So what we do is using renormalization theory, we can estimate for any given cell size the average magnetization of the cell size will decrease as a function of the temperature. Other magnetic properties like the anisotropy and the exchange are also a function of temperature. So that allows us to use 2 nanometer cell size as opposed to 2 angstrom cell size. And all of that produces a very dry plot, just like this one. I show it like this because what we try to do is mimic the experiment as much as possible. And what we're trying to understand is what performance different heads and media give us. And again, this is track density versus the linear density. All of these different points are different NFT widths or designs, different media with different grain sizes, and different reader resolutions. What we're trying to do is get to this upper right quadrant. The most we've been able to model without really having to change the architecture of the system is about 4.5 terabit per square inch. So it's over 8 terabyte per disk, which would be 80 terabyte drives if there were 10 disks in a drive. This is assuming that we're just scaling the components, and assuming we can scale them so aggressively, we think maybe 8 terabyte per disk is possible, or 4.5 terabit per square inch. But we don't really want to stop there. We want to understand how to go further and further. And really, what we want to do is not have to rely so much on the component scaling, because as the components become smaller, it becomes much more difficult to maintain the reliability of the system and to fabricate as many good components when we're really pushing the geometries. And I'll just mention that getting just one of these points is not just one simulation. It's hundreds of simulations because you have to optimize the bit length, you have to optimize the track pitch, and you have to optimize the laser power that's going into your NFT to figure out what is the ultimate capability of these combinations. I want to get to 10 terabyte per disk. What does 10 terabyte per disk look like? I mean, we modeled 4.5. If we wanted to double that, we're talking about 5 nanometer bit length, So 5 million BPI, 2 million tracks per inch, so 13 nanometer track pitch. Grain pitch has to be 5 nanometers because my bit length is 5. So my grains have to be at least 5 nanometers in diameter. But also the grain size distribution has to be pretty narrow, because if I have very large grain size distribution, then some of the grains will be really large, may not be ridden properly. Some of them will be small, will be overridden. So not good unless we have very good distribution. It'll be 2 grains per bit, so another reason why we need good grain size distribution. The thermal gradients are going to be much higher. This is more than double what we have today, because we would need to scale the geometry of the near field transducer, which will naturally lead to higher thermal gradients. And then the reader resolution will have to be much, much smaller than it is today. So we would need readers that are much smaller than 10 nanometers to be able to achieve these resolutions. So if we were to keep the architecture the same, the requirements for 10 terabit per square inch don't look very achievable. Some of the challenges to being able to achieve this 10 terabyte per disk without changing the drive architecture are head media spacing. So as we reduce all of these geometries, if we don't move the head closer to the disk, then the resolution will not increase. The thing is, it's not just we have the recording layer and then we have the NFT right above it. There's all of these protective layers on top of the media, on top of the head, in addition to the air-bearing surface that create physical space. And these layers have to be there in order to protect all of these different components. So we're trying to figure out what kind of novel materials can be used. And that's a pretty important and critical research issue for us, reducing head media spacing, because even if we reduce all of these geometries, that could very well be a limiting factor. Harped about grain size reduction. Have demonstrated 5 nanometer grain size, but it's also a matter of ensuring the distribution and properties is tight, and also the distribution in grain size is tight. And again, that's a very active research area in our recording media design center. And reader scaling is perhaps one of the more concerning issues. If we reduce the size of the reader, which we need to, no matter if we have any other recording technology and if we have very small grains, if we don't have readers that are narrow, we will never be able to keep pushing the track width as much as we want to. So coming up with novel designs to help push these geometries is really key for us. So we were looking at a lot of different options, and I'm not going to talk about a lot of them today. I'm going to mention some of them. But our goal as a research organization is to fill this funnel. So the wide end of the funnel, I'm not showing all of the designs here that we're looking at, but some of the more interesting ones to show you. We want to fill the wide end of the funnel with as many ideas as possible. That means that there's not a ton of resources on each of these. These are very immature, very high-risk ideas that we're really exploring in the university research space, or we're doing some fundamental modeling. And as we evaluate these different ideas and we determine that they can go from more of a idea phase to a feasibility phase, then we can start ramping up our activities, start doing more fundamental experiments in-house, start building some of the components, and then eventually hand off these ideas to actual product development groups. Some of the interesting ones I'll talk about here that could really help increase areal density and capacity are multi-level recording and multi-layer media to enable multi-level recording, vector recording. I'll explain what this all means. Novel readers like the non-local spin valve, I'll talk a little bit about other ideas that could help that we're looking at, very highly speculative, but still we need to do some research, are optical magnetization switching. So what if we can change the state of the media by just applying optical pulses? What if we can replace the magnetic material with a ferroelectric material? That is very far into the future. And the reason this is interesting is because magnetic materials, they have very strong exchange. So there is a limit to how small I can make a bit. At some point, I need to physically separate the bits. With ferroelectrics, it's possible that we could have unit cell size bits. Very highly speculative, and it's an area of research that we're interested in. But it seems to be the most obvious, not obvious, but the technology most likely to intercept a hard disk drive type device. You could still have a rotating disk form factor, potentially. You could still have a head flying over it that could write and read information. All of this highly speculative, but something that's in the research phase. And I put DNA in there because at some point we're looking at DNA as a potential information storage technology. As far as we're concerned, it's unlikely to be a hard drive replacement. It would be in some other performance tier, perhaps archival, but still something for us to keep looking at. Also not here is optical storage, like storing information on optical disks, for example. Again, we don't see that as a hard drive replacement. It's in a completely different performance and cost tier, so perhaps an archival technology. So, but anyway, I'll talk about some of the technologies that we're looking at to extend heat-assisted magnetic recording. Because as far as we're concerned, we want to leverage our existing technology as long as possible before we have to go to a completely different architecture and change our entire manufacturing process to accommodate that new technology. Multi-level hammer means, what if I have a recording medium and I can store information on different layers within the media? So leveraging the out-of-plane direction. And I think it's obvious why we want to do this, right? Because now I wouldn't have just 2 levels. I could have 3 levels. I wouldn't have just -1s and 1s. I could have a 0. And if I have more than 2 layers, potentially I could have intermediate states, maybe -1, -0.5, 0, 0.5, and 1. Very challenging architecture. First, from a media design perspective, we have a project with the National Institute of Material Science in Japan, and they're looking at how do you fabricate even 2-layer media is challenging. Iron platinum requires very high temperature deposition process, and if you try to fabricate 2 different layers with some kind of material in between, that's very challenging from a manufacturing perspective. But they're off looking at that. When they figure that out, then at least we have the media side of it. We need to figure out how to write the different layers. You could have each of these layers have different properties, so you could have the writer record information on 1 layer under certain conditions, and then write it again, pass again to write the second layer at different conditions. So you could have a 2-pass write. That's not ideal. Maybe there's a media structure that allows you to write different states by passing the writer just once. Those are projects that we have ongoing to understand how do we design a media and how do we write to it. But the biggest issue, again, going back to readers, I used to be a reader designer, so I feel justified in harping on the readers. It's a highly interesting area of research because it's actually very challenging to try to understand, how do we keep decreasing the size of these different sensors. But so even sensing two states becomes challenging when the geometries are so aggressive. But if I insert a third state, now I have 3 different levels to resolve. So the reader SNR is now a lot less because now I have 3 levels to resolve. And if I have intermediate states, that's even more levels. So being able to bring a multi-level system into reality requires invention on the media, the write, and the read side, even though this is, again, still heat-assisted magnetic recording. But if we were able to do it, that means we can relax the in-plane geometry, because now I have multiple levels out of plane. I can make the bits a little bit larger in plane. So that relaxes things like the grain size. So maybe I can get the 10 terabit per square inch with something like multi-level. And we're also looking at advanced reader architectures. Today's readers, there's a lot of the structure at the air-bearing surface. It's kind of large. You have the active layer, and then you have all of these other layers needed to generate the signal. So if I could have just one layer at the air-bearing surface, shielded by all of the different shields, then that improves my downtrack resolution significantly. So there are different ideas to be able to do this. What if I could move the sensing structures to further up? That means I can bring the shields closer to the active layer. So we have a university project with the University of Minnesota looking at that. Anomalous Hall effect reader, maybe we can have a novel material be that sensing layer, and then we'd only need the one sensing layer. Graphene is something that people want to slap it on everything, and it could do everything. Recently, people have measured magnetoresistance with graphene. The reason this is really compelling is that graphene is not magnetic, so if I decrease the geometry, there won't be any thermal noise. Could be a host of other issues. Mainly, we don't know how to integrate it into our current head manufacturing process, but it's a research project, high risk, but potentially very high reward, because if we're able to make a graphene sensor, then the geometries we could really push that. Vector recording is something that I'm really interested in, because I think that could really open up the space as far as being able to do like a multi-level system without actually doing multi-layers. Right now, so these are 2 different tracks magnetized in the same direction. So what we do today is we have a reader, and it senses the perpendicular field. So our reader design can only sense the perpendicular field, and the tracks are written to produce strong perpendicular fields. But let's say these 2 adjacent tracks are magnetized in different directions. That means you have these closure fields, and you have a very strong in-plane field. We don't have a reader that can sense these in-plane fields. But if you could, then you could use, in addition to these perpendicular fields, you could use these in-plane fields. And these in-plane fields could be across the track, it could be down the track. So if you could have readers that are biased in order to sense these different field direction, then that's another way to be able to do kind of a multi-level system, because within the same area, now you have all of these different fields and different states. We actually made readers that sense these longitudinal fields some time back, and it demonstrated the concept. But since they were just our regular readers biased differently, they didn't have the resolution we needed. But there's still an area that we're really interested in, and we're funding university research and starting to do more internal work on it. You know, all of these things, we're really collaborating with a lot of universities like MIT, the University of Minnesota, NIMS in Japan, to really leverage all of the knowledge that's out there, different research groups, and they have a different perspective than those of us that are working day in and day out in hard drive technology. Let's bring in different ideas from different fields to try to crack all of these challenging issues that we're facing. So hopefully today you are convinced that the data storage industry is the coolest place to work in, and that we're working on the most challenging problems out there technologically. Seagate is really excited to have released a brand new technology called HAMR that we think will really start a new S-curve and be able to take us to hopefully 100 terabyte drives and beyond. And like I said, we're really working with universities. We just started some projects with MIT and other universities to explore some advanced concepts that I think will be very beneficial to us in the long term. So anyway, thank you all so much for your attention.
Thank you. So now the talk is open to questions. So, yes.
So when you have laser to heat up your disk. Can you use the mic, please? So when you have laser to heat up your disk, what is the way to effectively dissipate that heat so that it doesn't further affect the magnetic order?
Right. So I mean, the head is designed with features to ensure that the head and the media are designed so that the thermal spot is very well confined and it doesn't bleed too much into the areas that you don't want to affect. So yes, details I can't really talk about, but yeah, that's an active area of research in the design space, writer design space.
Thank you.
I know this is probably related to the change in infrastructure that you mentioned, but I was wondering, when we reduce the grain size, we scale down, we would eventually, like in 1 to 2 orders of magnitude, reach the atomic size. How do we scale down further after that? What do we do after that?
Well, I don't think with magnetic materials you can get that small. So it's, again, an active area of research. People think that the smallest grain size you can get while having good properties is 5 nanometers. If it's granular media, then you have to record multiple grains per bit. So this is a project that we're working with Carolyn Ross on, is to increase the order parameter in the media. So can we make it more ordered? Can we improve the grain size sigma to be able to reduce the number of grains per bit? Something I didn't include the slide because I don't think I had the time, but something that we worked on for many years was pattern media. So can I use photolithography to define my bit size? And we demonstrated 5 teradots per inch. We couldn't record any information on it, but it demonstrated the process. And we were able to record information on pattern media that was lower density. But for magnetic materials, you can't just write information on individual atoms because that exchange is so strong, right? Hence, are there other materials where you can individually write either atoms or small clusters of atoms? So that's where the ferroelectric recording or some other advanced technology comes in. So yeah, we're trying to figure that out.
Sorry. Regarding the multi-layer that you were talking about in the advanced research, is it possible to penetrate those layers using signal at different frequency, even RF? I mean, according to you just need to heat it up, right, for specific depths. Yeah,
I mean, you could have different Curie temperatures, right? And you could write at different temperatures.
So according to the theory of black body radiation, right? If you have signal, let's say RF, that you emit on this area, it can penetrate at different depths.
Right.
So if you just hit that layer, and then you magnetize it.
So most likely, if I understand your question, are you asking will I erase one layer when I try to write the other?
Yeah, I mean, just try to pinpoint the specific depths that you want to heat up.
You don't pinpoint the specific depth. I don't believe we can do that. So, for example, if you're trying to write the bottom one and it has different magnetic properties, you write the bottom one, but you're also writing the top one. But then the writer would go again at a lower temperature and only affect the top one. So that's one possible way to write the different layers. Because you could write either top or bottom or whatever. One would have a lower write temperature than the other. So it doesn't work very well. You actually don't write good patterns if you do it this way. I think NIM's published some of this. We've looked at it before. Even if you, so you write one of the layers at a high temperature, there's still features of that track in the top layer when you try to write it at a different temperature. So it doesn't really work. What we have looked at is if you have an antiferromagnetic coupling between the layers, maybe you can write the zero state by not applying a magnetic field. So that's something that we published previously before. That is still, I said the read back is the biggest issue, but we still don't know how to write on media like this yet. Does that kind of answer your question?
Yes, sort of. Thank you.
Sure.
How big of a concern is material degradation?
It is a concern, yes. Reliability is one of our key metrics, and we're operating at very high temperatures, so ensuring the robustness of the media and the writer and all of these overcoats is an active area of research at Seagate.
Okay, let's thank Stephanie again. Thank you.